Hello, class. This is Lab 4, and I'm going to share a screen with you so that we can look at this. Yep, that's the one I want. Okay, right there. Now, what I want to do is, this is at this location right here. But the best way to get to this is to Google Energy State Park. Energy State Park, PHET, and that will bring up a Google. Well, yeah, it'll bring up the Energy State Parks, Colorado State University, I think it is. Anyway, I want you to go to two things. First of all, we're going to go to the intro. On the intro, I still have it running. It's like a pendulum, isn't it? And I think everybody can see that if you put the pie chart, the bar graph, the grid, and the speed up, and you have the mass there with absolutely no friction, it's just like swinging a, rock, a heavy rock back and forth, and eventually that heavy rock, due to air resistance or whatever, will, decrease and not be swinging anymore, or be swinging less. Here we are in like outer space, though, because we have absolutely no friction whatsoever, and you can see that we're just changing potential energy into kinetic energy to potential energy. I would like you to come here first and to look at this and to see what the frequency is. Now, look at that. You find what the frequency is, how long that's taking, and then I want you to change the mass. See how this is going back and forth? Let's change it. Let's make it a very small mass. And as you can see, the skateboarder gets smaller, doesn't he? But does the frequency change? Let's give him a really heavy mass. And in fact, I think I mentioned this, about with the pendulum. Does the mass change? So let's give it a very heavy mass. Now he's a really huge guy. He's going back and forth, but does the frequency change? There's more potential and kinetic energy exchange, but does the frequency of the oscillation change? Does the maximum speed change? Look at our speedometer up here. We're going to about that point right there, right about here. I'll see if it gets there. No, not quite. So about right here. Okay, so let's change the mass now. Let's make that mass much smaller. Oh my God. So that's what I want you guys to see, is that the frequency of motion and the speed at which it's occurring, irrespective of whether it is a very large mass or a small mass or a mass right in the middle, is, well, I'm going to let you make that decision. Now, the second thing that I want you to do is I want you to go to the friction part. That's number 2 in the intro, and then you go to the friction. Now we've got friction that's working here. And what I want you to do is I want you to take this guy and put him right up at the top. Now leave it exactly how it comes up. As you can see, I've got friction and mass the same. But what I've done is I put it into slow motion. I'm going to go back to normal motion right now so that you can sort of see what's happening, right? So just leave mass and friction exactly like you remember it. Now I'm going to bring this guy up here at the top. And he's going to experience friction. Now, of course, friction is only working due to the frictional coefficient on the normal force. So as you can see right now, he's almost horizontal, isn't he? So if he's almost horizontal, then he's not going to have a large normal force, and you'll be able to see with the thermal that, the only time that thermal is really going up is when he's in the bottom of those grooves. Let's do that again, just so I can show you how the friction. So he's going down, bottom of the groove, right? Then thermal comes up a lot when he gets to the bottom of the groove. Let's do it in slow motion so that you can see it a little bit better. Right, he's coming down, his speed's going up. He hits that first indentation. His normal force is up and down, and a lot of thermal agitation. The wheels are at the bottom, so that's where the thermal increases. But here's what I want you to do. I want you to look. I want you to take him up here. Now, he has kinetic and potential energy, doesn't he? And we know that work energy is force times distance. Now, the only force that's slowing him down is the frictional force. But the frictional force is not linear, right? It's not linear because he is not vertical. So what I want you to do is I want you to come up with an average kinetic, and I say kinetic coefficient of friction because he's moving all the time, isn't he? So I want you to come up with an average kinetic coefficient of friction for the skateboard rider in the mass being in the center, the friction being in the center. Excuse me. And then you're going to have to find the distance that he's traveling. Now you can approximate that. Right? You can approximate it with triangles, can't you? And this is more or less a straight part right here, isn't it? Right? And then that's a straight part. And then this is a straight part. And then this is pretty much a straight part too. So you should be able to find out him going that far and what the distance is of that, right? Because you have the grid, and the grid can show you the distance in meters. Remember this, all of the grid is in meters. So I want you to come up with an average thing there, all right? I might try to get this. Just a second. Where am I? I'm going to have to get out of here. Okay, I'm back. That was actually one of the students about a test. Not in your class, in the other class. So that is the lab number 4. Not a hard lab. I just want you to, look and see how the pendulum things goes, and then go to the second one that's friction. Leave it in the center, and then see what the frictional. Remember, kinetic energy 1/2 mv squared. Potential energy, mass times gravitational constant times the height above the datum plane. Frictional energy that's slowing you down is the frictional force times the distance it's working over. Frictional force, force times distance, that's energy. And that's what you're going to have as he's going down, right? There's more, obviously, but I want the average kinetic friction over that, first cycle. I shouldn't say first half cycle, I guess, of him going down over the two things and then back up again. That's what I want. The average frictional force for that first half cycle that he goes through with the friction at 1/2. All right? All right, I'm going to put this up and send it out. See you later.